In this video, we're going to talk about resonance structures. Resonance structures occur when you have more than one solution to the Lewis structure that you're drawing. So let's take something like benzene, C6H6. We draw 6 carbon atoms, 6 peripheral hydrogen atoms, populate with our valence electrons, draw our initial bonds to each of the periphery atoms, what we're left with when we get done with just doing the initial first bonding is 6 unpaired electrons on each of the carbons. So 1, 2, 3, 4, 5, 6. Now we plan on pairing up these electrons, but we need to figure out which way we want to pair them up because there's actually 2 configurations in this drawing. So let's say this top carbon is number 1, the second carbon here is number 2, and this third carbon here is number 3. We had the option of forming the first carbon-carbon double bond between carbon 1 and 2. So we form this bond, we pair these 2 up, and we pair these 2 up. This will be our first structure. But let's say we go back to our initial drawing. We have our 6 unpaired electrons. And now we decide that instead of forming an initial bond between carbon 1 and carbon 2, we're going to form a bond between carbon 1 and carbon 3. So we've got a double bond here, and double bond here. What's changed is the double bonding between the carbons. In the first structure, we had a double bond between carbon 1 and 2. Now we have a double bond between carbon 1 and 3. So what's the reality? Which one's correct? Well, the answer is that both kind of are. What we see when we have multiple resonance structures, different Lewis structure solutions, we actually get an average of them. So in reality, these are all kind of look like 1.5 bonds. And so actually when we draw the Lewis structure of benzene, we don't actually represent each of these as solid double bonds or single bonds. What we draw it with is a resonance structure showing that these bonds are all kind of somewhere between 1 and 2. So let's take another look at another example. Something like nitrate or nitrite. So nitrite is NO2. And we have 2 configurations for this as well. But in this case, let's draw the oxygens with different colors. Now in one Lewis structure, we have a double bond between the red oxygen and the nitrogen, and a single bond between the nitrogen and the black oxygen. Our other resonance structure is the red oxygen with only 1 bond between oxygen and nitrogen, and a double bond between the black oxygen and the nitrogen. So, as I said before, we have the 2 solutions. In principle, it's going to be an average between the 2. But let's say, for whatever reason, we have an isotope here. So typically, oxygen is isotope 16, atomic weight of 16. But we also have the option of oxygen 17. And let's say, for sake of argument, that nitrogen having a double bond to an isotope 16 oxygen is much more favorable than oxygen having a double bond to an oxygen 17. So even though we see both expression, we see both resonance structures, if we say that this is the less favorable configuration, what we're going to see is that actually the nitrogen spends more of its time in the other configuration, the lower energy configuration. So even though we're seeing an average, the average is weighted towards the lower energy structure being the most favorable. Now, one other thing to keep in mind with resonance is that when we draw arrows, there's a specific resonance arrow. And this is the double-headed arrow. If you ever see a single arrow with double heads, you're referring only to resonance. It's not a reaction, it's not implying any making or breaking of bonds occurring. What it's telling you is that there's more than one Lewis structure. And actually what you're seeing is the average of all these different Lewis structures, again, weighted based on their energies, with the most energetically favorable molecule being the most favored configuration.